Welcome to a high scores guide through Putnam. In this video, I'll explain a 2014 problem for a Putnam exam. The Putnam exam is taken every year by undergraduate college students and is known for how challenging it is. The goal of this video is to mainly empower high school students who have taken or are in the middle of taking their first calculus class. Especially for me, who's someone who just graduated high school, I felt lost when I tried to expand my mathematical knowledge on my own, because standard explanations of interesting problems like these often require assume a considerable amount of background knowledge. So I thought I would make this problem more approachable for people like me, and I hope you enjoy. So the problem is prove that every non-zero coefficient of the Taylor series of 1 minus x plus x squared times e to the x about x equals 0 is a rational number whose numerator, in lowest terms, is either 1 or a prime number. So if you didn't get the question right now, don't worry, I'll be constantly reading it throughout the video. So now onto the toolbox, or the tools that we'll be using to solve this problem. It's just the basics of derivatives. So of course the power rule, so derivative of 4x squared, you bring the power down and then you subtract 1. And that the derivative of e to the x is itself, and that's the property that e to the x is really famous for. Basic trig functions, that derivative of sine is cosine, and the derivative of cosine is negative sine. And that the product rule, so when you take a product rule, it's the derivative of the front times the second, and then the derivative of the second times the first function. And if you want to brush up your calculus, I encourage you to just pause on the slide. I've made sure that all the examples kind of match perfectly what you would need to be aware of in order to understand the next coming problem. And the last thing they kind of have to understand is factorials and the concept. So factorial is just multiplied down to 1. So 4 factorial is 4 times 3 times 2 times 1. And 7 factorial takes every number and just multiplies it down to 1. And in general, n factorial, which is doing n times the number below it all the way down to 1. So when you see an exclamation point, think factorial. So how this will be set up to kind of explain this problem. So first, I'll be explaining what a Taylor series is. That's the core of this problem. And then once we know what a Taylor series is, we'll find the pattern that this problem presents, and then eventually formalize it into a proof. So this is your guide to the galaxy of this problem. To begin to wrap your head around the concept of what a Taylor series is, I want you to first consider this fact, that every function can be written as a polynomial on a closed interval. This is known as Weierstrass approximation theorem. In Desmos, I devised a demonstration of this fact. So here I have e to the x times x squared plus 1 graph on the interval from -2 to 1. And we're going to try and approximate that with a polynomial. So first, let's just put maybe some x cubed plus x squared, then add some transforms, and then a y transform, and then eventually an x transform. And now we have a polynomial that approximates e to the x times x squared plus 1 on this interval that doesn't have the e to the x. It's just a polynomial. And the concept of Taylor series kind of branches off of this conceptual idea. The key difference between a Taylor series and our previous example is a Taylor series asks, well, what if we have an infinite number of polynomials that can map the overall function? So as an example, we have sine can be approximated as an infinite set of these polynomials. That would be cosines, these are cosines, and then e to the x. So think about it that the next term for sine would be x to the 9 over 9 factorial, then minus x to 11 over 11 factorial. So all of these functions can initially approximate an arbitrary function like sine or cosine. So for example, if we have, you can see these gifts here, this is sine being approximated. As you add more and more terms, it approximates more and more of the function. And theoretically, if you had an infinite amount of these polynomials, it would perfectly map the function over the entire domain. And here's e to the x, and the more terms you add, the better it approximates the function. So now the logical question is, well, this is a cool fact, so how do I actually make them? And the idea is that you continually take a derivative over a center point. So if you can imagine what a derivative is how a function changes over time. So it kind of makes sense that if you continually take a derivative, with each derivative you gain more detail in like how a function is fitting because it's matching the change over time more precisely. So for example, this is once again the the Taylor series for sine. And how you would make that is first you would just f of 0, which is 0, because the sine of 0 is 0. And then you take the first derivative and evaluate it at 0. So the first derivative of sine is cosine, and the cosine of 0 is 1. So 1 times x to the 1 over 1 factorial, which is just ends up being that x. And then take the derivative again, which just gives 0 because sine of 0 is 0. And then you multiply by x squared over 2 factorial. And then once again, you take the derivative again and evaluate x0, negative 1. And that would give you that term, negative x cubed over 3 factorial. And you just continue the process, giving you these next 4 terms that initially goes down to that. So keep in mind this general form of a Taylor series, and we'll continue to work with that in a bit. Now for a minor point that really what I've been showing you now is what's called a Maclurin series. And the Maclurin series is a specific form of the general Taylor series. And in a general Taylor series, you can center it wherever you want. So as you can see, another infinite polynomial that would describe sine would just be centered at pi over 2. So I shift everything over for pi with x minus pi over 2, and then I take the derivatives at pi over 2. And you can see in this GIF over here that it's creating the sine graph based off the center of pi over 2. And the Maclurin series just specifically takes the derivative at 0. That's just more of a minor point that I want to point out, and a small thanks to Desmos for making the creation of these GIFs so easy. And this is kind of more important because the question itself specifically states we're taking the derivative about x equals 0, and that's kind of the hint that you were doing a Maclurin series instead of the broader Taylor series. You're taking the derivative only at 0. So now let's actually do an example Maclurin series, or really a Taylor series at 0, to kind of wrap our heads around building these things. So we're building an infinite polynomial to map the function e to the x times x squared plus 1. So our first step, f of 0. So f of 0, if we just plug it in, we can see that we get 1. Now we need to take the first derivative and evaluate that at 0. So that would give us the first derivative. If we apply the product rule, e to the x kind of preserves the initial state because the derivative of e to the x of itself, and then I plus e to the x times the derivative of x squared plus 1, which is 2x, and that simplifies down to that, and that evaluated at 0 is clearly 1 because e to the 0 is 1. And now we're just going to do the same thing for a second derivative. So e to the x times x squared plus 2x plus 1, because the derivative of e to the x is itself. And then we need to take the derivative of this piece, which is 2 to the x plus 2, factor out the e to the x, that simplifies to that, and the second derivative is 3. So now that we kind of know the derivatives, we can just plug into this Maclurin series formula. So as you can see here, we have these derivatives, and now it's just plug in sub. So we know that e to the x times x squared plus 1 can be written as 1 plus x over 1 factorial plus 3x squared over 2 factorial. And if we just continually take in derivatives, it's easy to see that we can just continually make these polynomials, making a better and better approximation of e to the x times x squared plus 1. And that simplifies down to 1 plus x plus 3x squared over 2, and just goes on forever. So now that we have a rough understanding of what a Taylor series is, I want you to take a new look at this problem. This problem says prove that every non-zero coefficient of the Taylor series of this function 1 minus x plus x squared times c to the x about x equals 0 is a rational number whose numerator in those terms is either 1 or a prime number. So what you're trying to prove is that the coefficients of this Taylor series, so the general form, the coefficients of a Taylor series, would be the derivative divided by the factorial. And you're trying to prove that the numerator is always either going to be 1 or a prime number in simplest form of this overall coefficient. So thinking about that, and I'll give you a hint. What the key to this problem is finding a pattern in the numerator. A pattern is specifically the derivatives evaluated at 0. So I encourage you to take out a piece of paper and try and take the derivative of this function and try and find the pattern in the numerator and then prove this problem. But now let's go on with the problem and let's make the Taylor series. So now let's find the pattern, and particularly the derivatives, because that's what the numerator is in a Taylor series or Maclurin series. And I have the question right down there so we don't lose our focus, and we want to focus on the numerator. So of course, let's evaluate the function first. So f of 0 is of course 1 because e to the 0 is 1, and then 0, 0, that leaves a 1. So finding the first derivative, using the product rule, the derivative of e to the x is e to the x, and then writing out the first piece, and the derivative of the second piece is 2 to the x minus 1, so the e to the x. So then we can just factor out the e to the x, and that's the first derivative, and evaluating that at 0, that's of course just 0. So now, using our first derivative, and we're gonna find the derivatives of the rest. So for finding the second derivative, once again, just the product rule, the derivative of e to the x is e to the x, and saving the second piece, which is x squared plus x, taking the derivative of x squared plus x is of course 2x plus 1. Factoring that out, we have left with e to the x, x squared plus 3 to the x plus 1, and that evaluated at 0 is just 1. Taking the third derivative, we see once again product rule, the derivative of e to the x is it's just itself, so that preserves x squared plus 3 to the x plus 1. Now taking the derivative of the second piece and multiplying by the original e to the x gives us 2 to the x plus 3, because the derivative of x squared is 2 to the x, and 3. Factoring that out gives us x squared plus 5 to the x plus 4. Evaluating at 0 gives us 4. Okay? And finally, doing this one more time. Once again, product rule, the derivative of e to the x is just itself, then x squared plus 5 to the x plus 4. The derivative of that is 2 to the x plus 5. Factoring out again, leaves us with that, and that evaluated at 0 is 9. So the key things to notice is what is happening every time. Well, because the derivative of x squared is 2 to the x, it's incrementing by 2, and the constant defines the functions at 0. So when I plug in 0, all that's left over is always the constant. So it's the 1. When I plug in 0 here, it's a 4. When I plug in 0 here, it's, of course, the 9. So now that we have all these derivatives, it's time to put on our number theory hat and find the patterns in the derivatives evaluated at 0, which is the numerators of the Taylor series. So now, first, let's take a look at the x values. So the x values are, of course, just negative 1, 1, 3, 5, and 7. They're going up by 2. And the actual derivative values you can see here, and it's just the values of the constants as previously stated in the previous slide. So now let's try and look for a pattern in the derivatives, which are the numerators of the Taylor series. So I'm going to show you a couple of the next terms. So the next terms would be 9 and 16. And the terms after that would be 11 and 25. And this is how long it took me to notice the pattern. Initially, when I was solving this problem, I went out to the sixth derivative. And you can see here that there's a curious pattern in the derivatives. Once you get to the second one, they're all squares of the previous number. So when I have 3, it's 2 squared. When I have 4, it's 3 squared. 5, 4 squared, and so on. And why is this pattern here? Well, since the derivatives are all squares, let's think about what's happening. Well, e to the x is preserving the original function every time. So for example, when I take the fourth derivative, the derivative of e to the x is just itself. So then I just multiply by the original function each time. So effectively what's happening every time I take a derivative is that I'm adding on a 2 to the x, because the derivative of x squared is 2x, and I'm also adding on the previous x value, because if we look at the third derivative, the derivative of 5x would of course be 5, the derivative of 3x would be 3. So you're always adding on the previous x value on to the previous constant. And it's because of these facts that you can see that every time the constants are being added together. So for example, I have 1. And then 1 is getting added on to the x value of that, 4. And then 4 is getting on to the x value of that, 4 plus 5 is 9. So effectively what we have is 1 plus 3 is 4, 1 plus 3 plus 5 is 9, and we're adding up consecutive odd numbers. And that's because the derivative of x squared is 2 to the x, and it's increasing, it's incrementing the x values by 2, and because of the product rule, the previous function is always preserved, which allows for that incrementing and allows for the previous value to always be added on to the next value, and this is causing this almost creation of this odd recursive formula. So why are these odd values always adding to squares? And this is a curious mathematical fact that when you add up consecutive odd numbers, you always get squares. And just to give you a quick visual proof of that, 1, then 3, then 5, and 7, and you can see that it maintains its square-like structure. Forgive my crude drawing. But what this shows us is that the derivative of this Taylor series will always give us squares. The third derivative will be 2 squared, the fourth derivative will be 3 squared. And we found this easy pattern that we can then use to solve this problem. Now that we have this pattern in the derivatives evaluated at 0 for this function, forming the Taylor series is really easy. It's just after you do the 1, 0, 1, you can just do 1 minus the power and get the square. So 3, it'd be 2 squared over 3 factorial. 4, it would be 3 squared over 4 factorial. So it's easy to see how the coefficients will grow. So now let's move back to the question of the numerator in lowest terms of this coefficient, which is the squares over the factorial, has to simplify to either a 1 or a prime number. So let's focus on one of these terms, specifically the 4 squared x to the 5th 5 factorial. So focusing on this one term, let's think about what's happening. So we have a square, 4 times 4, over a factorial, and remember from our prerequisites, it's just multiplying down to 1. So we see clearly that the initial 4 cancels, and we're left with this in terms of the coefficient, and then the 4 divides the 2, and we're left with a prime on top. So in simplest form, a prime is in the numerator of the coefficient of this term. But now let's try and move toward a proof. And to move it toward a proof, we can't focus on only these small terms. So let's think about a bigger one. So technically, any bigger one would be formed through 1 minus the power. So how about we try the 21 power? The 21th term of this would have a 21, and then have a 20 squared. So thinking about what would happen, we would have 20 times 20, and the initial 20 would cancel with the factorial. And now we need to say, will this 20 cancel out to a 1 or a prime? This is a bit confusing to think about, but I want you to think that you can write 20 as any two distinct numbers multiplied together. So I chose 10 and 2. And is there a 10 and is there a 2 in the denominator? You can see clearly there's a 2 in the denominator, but there's also a 10. Because of the way factorials work, there's definitely 19 times 18, and there's definitely a 10 in there, and that'll cancel to a 1. So this just kind of gives you the broad overview of how this numerator always cancels to a 1 or a prime number. And now let's move over to a proof. Moving it toward a proof, now let's focus on why the coefficient for this specific 20 is going down to 1. Well, the 21 doesn't really matter. It's because a number will never really divide a number plus 1. So we can just get rid of that. And now I just write it like this. So why? We need to show that every time you have a number, n, let's just say n, over n minus 1 factorial, you'll be left with either a 1 over or a prime. So let's just generalize that, n over n minus 1 factorial. So our first thing is, if n is not prime, then it can be written as two distinct numbers, which will cancel out, leaving a 1. So for example, with the 20 in the previous slide, we did 10 times 2. We can do another example. What if we have 10 over 9 factorial? So with our Taylor series, we could have 10 squared over 11 factorial, and the first 10 would cancel out, the 11 wouldn't matter, and we'd be left with this. So extending, we could write 10 as 5 times 2, and of course the 5 and the 2 would cancel. It could be written as two distinct numbers, which would leave eventually a 1 in the numerator. In the other cases, well, n could also be prime, and if n is prime, then we've already completed our condition. So for example, our Taylor series for this one would be 7 squared over 8 factorial. Well, the first 7 cancels, and the 8 doesn't matter, so then we just have a prime over a factorial. So overall, this shows why this always works when you have n over n minus 1 factorial. That you always have, if n is not prime, it can be written as two distinct numbers, which will cancel out to 1. If n is prime, then you've already satisfied the condition of the numerator either being 1 or prime. So if n is not a prime, then there's a chance that it can't be written as two distinct numbers. What if it's a square of a prime? And we've actually run into this case before with this particular polynomial. So the first 4 cancels, and we can ignore the 5, leaving us with this. So 4 can be written as a square of prime 2. And cancels with the first 2. So even though 4 itself is not a prime, it cancels out to a prime on top. But this is actually only a problem when n is equal to 4, or really with 2. Because in any other case, so for example, with this polynomial, the first 9 cancels, and then we can ignore the 10, and we're left with this. 9 is, of course, a square with a prime, a square of a prime 3 squared, and it cancels out with the first 3. But we can't forget that within that factorial, 2 times that prime will always be present, and in that case, that would be 6. And then 6 can be written as 2 times 3, so once again, it would leave a 1 in the numerator. So 4 is just a particular caveat where even though it's not originally a prime, it will leave a prime in the numerator instead of a 1, and it's something we would have to account for in a formal proof. But with that, the proof is over. Now, since I know the last couple slides are probably overwhelming, let's just simplify this down to 2 critical points, or critical pieces. So the first critical piece is that the derivatives of 1 minus x plus x squared e to the x evaluate to squares at 0. So this is the pattern within the numerator that allows for this generalization. And we know that this simplifies in the Taylor series and Maclurin series. It's always squares over the factorial plus 1. And we've proved that that always yields 1 or a prime number, which proves this statement below. So because of the pattern in the derivatives and the way the Taylor series is laid out, all of the coefficients will be in this form, and we know that in this form, the numerator will always be 1 or prime number, which proves the statement below. So now that we finally proved the statement, I'd like each of you to take away 3 key things from this. First, the Taylor series are infinite polynomials that perfectly match functions that are infinitely differentiable. So if you can differentiate a function over and over and over and over again for infinity, you can form a Taylor series off of it that will perfectly match it. And the general form of Maclurin series of having the derivative over factorial is something to keep in handy. But really just in general, I want you to take away the process of proving. So what we did here was we understood the question. We spent a lot of time breaking down the Taylor series and how to derive, but then eventually we started finding the pattern. And once we started finding the pattern with the derivatives and forming squares, we were able to formalize that into a formal proof. So understand the question, find the pattern, and formula proof. Congrats, you are now in the unique subset of the population that understands how to solve a Putnam problem. Remember the mantra, understanding, then find a pattern, and then find a proof. Thanks so much for watching this video.